that gave us issues when we were working on it last time. And it turns out that it has something to do with the absolute value. And the absolute value and the initial condition have to match up. So if you look at the initial condition, if we take a look at the possible solutions, these things would have possible solutions that are either in the first, second, third, or fourth quadrant, but it doesn't go into, if it's in the first quadrant, then it stays in the first quadrant. And we could take a look at solutions by looking at the slope fields. And so what I did is I took this thing, to make this into a slope field, I needed to make this dy dx, or get dy dx by itself. So in one of those slope field applications, online applications, oh, I thought I changed it. I did change it, now it changed back. I could just type that equation in, or dy dx, assuming it's dy dx, and this is equal to, what is it, y minus or plus? Y minus x times y? Y minus, parentheses. Boy. Y minus x times y, close parentheses, divided by x squared. And then I have this possibility, or this is the slope field for that. And if you, this particular one, this particular program allows us to pick points just by clicking on the slope field. Sorry, I'm booting up my program here. So if I click on a point over here and try to figure out what the slope field is, wait, how's it go? Oh, left, the other left. Okay. Yeah, so I can click it over here, and drag it over here. So if the point is, what is it, negative 1, negative 4, negative 1, negative 4, then I have something that's completely on the left-hand side, and then that's my solution. Or completely in the second, third, the third quadrant, then that's my solution. When we worked on it analytically, I kept the absolute value on the x, but not on the y. So if I were to graph this, I see that my graph, or this particular graph, happens on the first and the fourth quadrants, right? Had I kept my absolute value on the y as well, then I would have covered everything, first, second, third, and fourth quadrants. And if I didn't put my absolute value around the x and just the y, then I'm only in my first and second quadrants. So the answer that they were looking for, since y was by itself, the answer that they were looking for was the answer where the x did not have an absolute value. And where x did not have the absolute value, this graph would describe the graph solutions between in the first quadrant or in the fourth quadrant. Okay, so the point 1, 4, or 1, negative 1, negative 4, falls on this graph where it's in the first or the third quadrant. In this case, it's in the third quadrant. That's the graph that we were looking for. So that's the correct solution. And in fact, Bianca typed it in without the absolute value, and it worked out. Okay? All right, so there's issues with the absolute value. Another way to test this out, whether you put the absolute value or not, is that if, say, you had the absolute value, and then you put in x is equal to -1, and you see that if you put x is equal to -1 with the absolute value there, that will make the whole right-hand side positive, and that would make the y positive. So with a -1 in for x, a -x, and then a positive y, I'm not in the correct quadrant. But if you take out the absolute value, then you are. Okay, so that was the issue, and that's the resolution, I guess, for this problem. I'm not going to put it in the notes, but it's recorded, so if you wanted to review that, you can review it. So meanwhile, we're talking about, not exact yet, but we're talking about the integrating factor and the first order linear differential equations. So I just want to highlight a few things. Let me just recopy a couple of these things. If you have a first order linear differential equation, you can eventually write your first order linear differential equation as a y prime plus some function times y is equal to another function. And then from here, I talked about solving for this using what's called an integrating factor. And the integrating factor is a factor that we find to multiply the whole differential equation so that it pretty much looks like a product rule. So we get the integrating factor, and then we multiply it through. So here's a general step-by-step procedure for solving for a first-order linear differential equation. If it's not separable, which I think is still the easiest method that we know, if it's not separable, then you can integrate it, or you can use the integrating factor. So put it in standard form, identify your px, and then find your integrating factor. Multiply the standard form by the integrating factor on the left-hand side and the right-hand side. Your left-hand side will look like a product, and so you just integrate both sides and then solve for y for the product rule. So that's the step-by-step process. And that's what we should take from this, and then we'll do a few more examples and see if we can solve for these things. Okay. So the examples are, well, I picked some examples in the book this time, so I don't do all your homework. And here are a couple of examples. So let's do, see if we can do number 12. So we'll start off with this equation, and what we need to do first of all is to put it in standard form so that the dy dx is by itself. All right, so let's do that. So we need to divide by 1 plus x, so dy dx is equal, or not equal to, minus. I have an x divided by 1 plus x times y is equal to x plus x squared divided by 1 plus x. So we can do some simplifying, a little bit of simplifying here, but we also need to be able to identify our p of x. And then if we want, we can, I suppose we can factor out an x here, right? X. So the whole right-hand side just becomes x, and that might be helpful later on. Okay. So now that I've identified my p of x, the integrating factor is, what was the integrating factor again? Mu of x is equal to so e to the integral of px so we need to take the integral of this. That doesn't look easy. Any suggestions? Put it into Wolfram alpha. U substitution? So it looks like I have a u du. What's on top? What? U minus 1. Okay. Remember when I took Calc 1, this is a problem that I got wrong on the test, this particular substitution. So whenever I teach Calculus 1, I always make sure I put it on the final exam. So anyways, now that we have this, we can break this up to 1 minus 1 over u, right? Which is easier to integrate. So that's u minus ln of u. And let's just ignore the absolute value for now. And remember the plus c's here, it doesn't matter because that's going to merge somewhere in the big plus c later on, so let's ignore the plus c as well. And let's throw it back with x's in it. So it'll be 1 plus x minus ln of 1 plus x. Oh, did I just say ignore the absolute values? It's like I want it to be absolute values. So that looks like a complicated integrating factor. I want to multiply both sides by this, right? So let's take our integrating factor mu. Oh, I need to raise it as an e. So still in green. Mu of x is equal to e to this thing. This is a 1 plus x minus ln of 1 minus 1 plus x. So let's see how this breaks down. This is e to the 1 plus x. I would say divided by e to the ln of this, and then that just becomes 1 plus x. Is that okay? You guys comfortable with the logarithms? The intermediate step here is e to the 1 plus x divided by e to the ln 1 plus x. And e to the ln of something is something, so that's just the denominator. All right, so now that's your integrating factor. And let's go ahead and multiply this on both sides of this equation. So I have e to the 1 plus x over 1 plus x times dy dx is equal, or not equal to, minus, I have to multiply that whole all the way through. I have e to the 1 plus x over 1 plus x times x over 1 plus x times y is equal to, now I have an x in here, so let's just say x e to the 1 plus x divided by 1 plus x. What a mess. Okay. Now, I'm just going to assume, since if we did this correctly, the integrating factor is there to make the left-hand side look like a product rule, right? So I'm just going to assume that it's a product. It's a product of two things. Well, product usually would be of two things. What are the two things that it's a product of? Yeah? 1 plus x and e now? So it's derivative of the first times the second, or let me say it this way. It's the first times the derivative of the second plus the derivative of the first times the second. To the 1 plus x over 1 plus x. So that's one of them. And then the other one is just y. Yeah, it turns out to be the integrating factor. Okay, and then what we have here on the other side is x e to the 1 minus x over 1, or 1 plus x over 1 plus x. So now we just have to integrate both sides and then solve for y. Right, those are the last two steps. Sure. Yeah, how would you integrate that? Right? So now let's integrate both sides. We know that the integral of a derivative is the original function, so the left-hand side is just going to be this mu integrating factor. And then so my last step when I solve for y, I'll just divide by that or multiply by the reciprocal. But now we have to deal with this thing. How would you integrate that? Wolfram alpha? Yeah, I would just use Wolfram alpha. I think you could do an initial U substitution, and then so that'll be e to the u divided by u, and then you change x to whatever it is, u minus 1. And then you can separate it and then work it out that way. Can you picture that? So if you let u equal to 1 plus x again, and then x is going to equal to u minus 1, just like you guys did before. This would be integral of u minus 1 e to the u divided by u. And then you can break this up to two different integrals. So you have e to the u, and then you have e to the u over u, and then whatever that turns out to be. What's e to the u over u? What? Yeah. Yeah, distribute and then break it up. So if we break it up and then distribute, this would be e to the u minus e to the u over u. And now we just need to figure out what this is. I don't know what that is. What's e to the u over u? I have to do probably some integration by parts or something. So I'm going to use Wolfram alpha. And do the whole thing. So I want to integrate. I have to be careful with parentheses here. X times e to the 1 plus x, and then divide by 1 plus x. What? Wow. Let's see. Let me try something. Well, what? I don't know. This is number 12. What? Webassign one? No, that's a special integral. Oh, because this is, at this point over here, this is a product rule. And so what we're doing is we're trying to get the original product before they took the derivative so that we can just take the antiderivative. It would, but when you take the derivative of this thing, because this is in the denominator, there's probably going to be a negative sign that would come up. So what you could do is to take this thing and then take the derivative of that and see if you get the same thing up there, and you should. So I don't know what to say. What? Is there a sign problem here?
No, Webassign.
Oh, Webassign? You want to do Webassign problem? Oh, come on. There's a possible trick here that you can use, and I don't know if it's something. What? Partial fractions? No. What? No, I don't think. I said integration by parts earlier, but I don't know if that would work out either. And so the only suggestion that I might have here is possibly dealing with this +1 business. And there's because 1 is a constant up here, if we get rid of that 1, it's kind of not important. And I don't know if that would make a little bit of a difference in the solution here, but it possibly could. And so I guess we'll think about that later. All right, well, no, not a U substitution there, but in this step over here, where we found the integrating factor, and the integrating factor was 1 plus x minus this thing. Because 1 is just another constant, we can just scratch that and make our integrating factor just this. And there possibly might be some hope in being able to integrate that a little bit better. Possibly. So that might be one way to solve for this. Could try it out, but it might not work, and then I would have wasted that time without knowing. So I can try that, and then, or you could try that and show me next time. But I'll have to come back to this again another time. All right, you guys want to see a Webassign? I suppose since I blew that one, we should take a look at a Webassign problem. And what section? This is section 2.3. I don't want to copy it. Is it 2.3? All right. Randomly pick a problem here. What? Which one should we do? You guys have any suggestions? The hardest one? Ah, this one looks good. Oh wait, this one is, I don't know if this will fit our mold yet. Let me think. No, I don't want to do that one. You want to do one with sine and cosine?
No.
Let's do one with sines and cosines. So they follow it up with give the largest interval, and then are there any transient terms? We'll talk about transient terms when we work this out. So let's start off with the differential equation that looks like this. We want to put it in standard form, so we need to get dy dx by itself, which means I have to divide by cosine. Now, cosine is 0 at like pi over 2 or something like that in different places. So we have to make sure that we identify that those points where the cosine is equal to 0 would be undefined because we're going to divide by it. So we have dy dx is equal to sine over cosine, or not equal, plus sine over cosine is tangent. So let's just go ahead and go to tangent x times y is equal to secant x. So this is our p of x, and we need to integrate the tangent function. Is that easy? No. This is all going to be hard. So our integrating factor, mu, is going to be e raised to the integral of tangent x dx. So what's antiderivative of tangent x dx? What? Say again?
Natural law of the absolute value.
Let's see. Okay. So if you have a table of integrals, that might be handy to have. Or if you kept the tangent as sine over cosine and did a U substitution, then it'll work out the same way. But it's better if you don't have this memorized. It's better to just have it on a sheet of paper that you can look up or whatever. So we'll say that this is the integrating factor, and that's what I need to multiply both sides by. So we have e to the ln of secant of x dy dx plus e to the ln of secant of x times tan x times y. Uh-oh. I'm out of room here. And then e to the ln of secant of x. Wait, what's e to the ln of secant of x? Why am I doing all this stuff? So, yeah, we should have just multiplied everything by secant of x. I remember I was teaching one time, I was writing this fast, and then I forgot the C for the secant, and then we were looking at that, and the students were saying, "What are you thinking?" Okay. Antiderivative. Well, we know that this is going to be the derivative of a product, right? And the product is going to be secant of x times y, and then the other side is just the other side. And so if you take the integral of both sides, we know that we just have a secant of x times y, and then now the integral of this thing. What's the integral of this? That's just tangent, right? So this is where you want to make sure you include the plus c business. And then now you're going to divide by secant to solve for y. So you get y is equal to tan x plus c divided by secant x. And and we have to remember that the secant will also have to go under that arbitrary constant and not just a tangent. You know what I mean? So be careful not to do it like this. Tan x over secant x plus c. Because when you do the division, you actually needed to divide all the way through. So this is not correct. And it does make a difference when the secant is under this arbitrary constant. I suppose you can leave it there, or we can multiply by the reciprocal of secant, which is cosine, right? And if we do that, what are we going to get? So multiply both sides by cosine x. Or top and bottom when I say both sides. So tangent times cosine is just sine, right? And then a constant times the cosine of x. All right, so let's try that. I hope it works. Sine x plus a constant times cosine of x. And they have other questions here too. Is that right? Okay, so that worked out okay. Give the largest interval over I, which a general solution is defined. Think about implications of any singular points. So we didn't formally define a singular point, but singular point is when you first divided by that. When we first divided by, what did we divide by first? Cosine x. So when we first divided by cosine x. Over here, so cosine x is equal to 0 are going to be your singular points. So x is equal to pi over 2, right? Cosine of 0 is not 0. Cosine of pi over 2 is 0. So pi over 2, and then plus or minus some combinations of pi. So these are your singular points. So wherever that is equal to 0 is going to be your singular points. So if we look at the number line, and we know that we can't have these points over here, then in terms of finding a good interval for ourselves, since we don't have an initial value, a good interval for ourselves would be basically between these singular points, right? Otherwise it could possibly go to infinity. And it looks like this interval is just as large as these other intervals, so any one of those intervals would do, and I guess we have a choice here. So 0 to pi, negative 1 to 1, negative pi over 2 to pi over 2, I think was one of the ones that I highlighted. So let's try that one. So that one looked like it turned out okay. And then it says determine whether there are any transient terms. So transient terms is another term that I didn't really define, but a transient term it's a term that goes to 0. So if you have a solution, your solution has several terms in there. If any one of those terms goes to 0 as you go off to infinity, then it's called a transient term. So if we take a look at our solution, we have two terms here. We have a sine x and a constant times cosine x. Does any of them approach 0 as we go off to infinity? The sine x just oscillates, and a constant times cosine x is just going to oscillate as well. None of them get squeezed down to 0, so if you had like an e to the negative x or something like that, that would be a transient term. But in this case, your graphs would just be oscillating. So your terms would just be oscillating back and forth, and none of them shrink down to 0. So it looks like here in this case there's no transient terms. So let's select none. And that looks like it's right. So that would be it. Okay? How'd that work out? Looks good? Better? Better than 15 minutes ago? Better than number 12? Yeah, some of those are the tricky integrals. There's constants that pop out, and usually you can merge them with other constants, and sometimes you might be interested in adding another constant to make your next integral step easy. And I think that's our key. Anyways, let's move on. So are we good with these types of problems? The integrating factor problems? It's a step-by-step process. We have the 4 steps to do it. By the way, if you do this enough times, you might be able to skip a couple of steps. If you know that your integrating factor, if you know what your integrating factor is, right, and then you end up multiplying it and then saying that this is a product, and then you undo the derivative by taking the integral, it turns out that on the left-hand side of your equation, after you do this, these 2 or 3 steps, then you're going to have your integrating factor times y left. Okay, so maybe you can skip over these parts where we're going to multiply it out and identify that it's a product rule and undo the derivative. Maybe you can skip over those steps and get to here right away. And then what does that do for your right-hand side? Your right-hand side is just the integrating factor times the original right-hand side after you write it in standard form. So it's the right-hand side times the integrating factor, and that's what you're going to have. The other integral that you're going to do would be that integral right here. Okay? Should we do another one? Or are we good with this? All right, let's do one more. Now that we can skip steps. I'm going to skip steps. I should really have you guys do it yourselves, and then when you're comfortable skipping steps, then you can start skipping steps on your own. All right, let's try this one. Solve for this initial value problem and give the largest interval. I don't know why I have that blocked out thing over here. Something about my pop-up blockers, probably. All right. Let's see if we could do this. This is y prime is equal to, not equal to, I keep saying equal to, y prime plus 1 over x y is equal to e to the x over x. Here's that e to the x over x thing again. Well, let's identify the singular point already, just in case it pops up. Because I divided by x, I have a 0 singular point. So whatever my largest interval is going to be, it's not going to include 0. So it's either just going to be positive real numbers or negative real numbers. So this is my p of x, and so I know that my integrating factor is going to be e raised to the integral of 1 over x dx, which is what? Ln x, right? So e to the ln x, which is just going to give us x. So multiply both sides by x. So this is the step that you would, these are the steps that you would eventually skip. I know that this is my integrating factor, and I know when I multiply that out, I'm going to get a product rule of some sort. And so I know that my product is going to eventually be the integrating factor times y. And so I skipped a few steps here. I already integrated my product rule, and so I'm going to integrate this as well. I also need to remember I need to multiply this by x. All right, so that's the 2 steps that are skipped or so. So we would cross out the x's, and the antiderivative e to the x is just e to the x. So my final answer is going to be e to the x. That's the antiderivative of e to the x. And then I need to divide by x to get y by itself. Oh, plus c. So that x is under both of them. And then if I want to solve for this, I have an initial condition. I'll put 1 in for x and 9 for y. So solving for initial condition, I have 9 is equal to e to the first power plus c divided by 1. So c is equal to 9 minus e. So it looks like my equation here, or my function, particular solution, is e to the x plus 9 minus e divided by x. Okay? Largest interval. The largest interval I can possibly get out of this is anything that does not have a singular point. So I have a singular point at 0. I know I can't have that. And my initial condition is on the, it's positive. It's on the right side, right? So x is equal to 1. So that's my initial condition. I want that to be part of my graph. So it looks like my interval is going to go from 0 to infinity, not including 0. And while we're at it, if I rewrite this equation as y is equal to e to the x over x plus 9 minus e over x. As x goes off to infinity, e to the x is going to get really large, so this is probably going to go off to infinity. But what happens to this? The x in the denominator is going to dominate the constant, so this whole thing is going to approach 0. So as x goes off to infinity, this term approaches 0. This is infinity, and this is 0. So as x goes off to infinity, this term goes to 0. So 9 minus e over x is called a what? Transient. Transient term. Okay? Should we check? I suppose we should check. All right, let's put in our answers, and oh man, I hope it's right. Our solution was let's put a fraction bar from the beginning here, and then the numerator is e to the x plus 9 minus e, and then our denominator is x. Do you guys check one answer before putting in the other one, or should we just put them all? Nah, let's put them all, hope it's right. 0 to infinity, and that's all they asked. They didn't ask for a transient term. Is it the whole thing or just INF? No. So INF is like one of those, if you do LaTeX underscore INF or backslash INF, it's infinity. But yeah, I suppose you can just type in infinity if you're a keyboard kind of guy or gal. Oh, look, it's right. All right. Are we good? Let's move on. Oh, I suppose I should actually identify that this is going from 0 to infinity. All right. The next section is, it's called exact differential equations. So differential equations have different forms, or different looking forms, different looks, different styles. And one form of a differential equation has it where the dx and the dy are separated. Instead of seeing the dy dx like we're used to, you can have it kind of separated, and there's a name for that. It's called differential form. And there's something special about a differential form, and in that it is a derivative of something. So if you've taken Calc 3 before, and I did mention this, that we're not going to do partial differential equations, but we do need to know a little bit about partial derivatives, and it's a simple concept where one of the variables is fixed, and then you take the derivative with respect to the other variable. And that's assuming that you have a function of two variables, like f of x, y here in this case. So what we have here is it's called a differential. And if we have a function of two variables, we have what's called a differential. And then it turns out that if you have a function of two variables that's equal to a constant, you take the derivative of both sides, on the left-hand side you have that differential, and on the right-hand side the derivative of constant is 0. And and for Calc 3 students, they would identify this as a level curve, and here the derivative of a level curve is 0, which means if you're looking at a level curve, you're not going to go up or down in your height. Okay. That's just for Calc 3 people who have taken Calc 3. If you haven't, then don't worry about it. Not a big deal. So this is our differential, and it turns out that there's a nice property where this would equal to 0. And that's how we're going to define what's called an exact differential. So the differential expression is called exact if essentially it's a nice function, and then the first order partial looks like this. And so now this expression over here, if we set it equal to 0, it becomes an equation, and there's a derivative that exists in here somewhere. And so we have, I went from expression to equation, a differential expression now to a differential equation. So an exact differential equation is something of this form, where that differential on the left side is actually equal to 0. So that's the definition of an exact differential equation. Okay, so there's another piece of information though that's important, in that we have to be able to, in order to try to solve for this, we need more information about the two functions m and n. And so that's going to come in a theorem. So let's take a look at the theorem that we're going to need. And the theorem that we're going to need requires us to do some partial derivatives, which again, the concept is fairly simple, I think. So the bottom line, we don't have to worry about this whole theorem, because this theorem actually would be living in Calc 3, and it's not a prerequisite for this course. But the bottom line is that if you have a differential equation of this form, where you have something dx plus something dy, those two somethings have to have a special, there's a special criteria for those two expressions. And that is if you take the derivative of the expression multiplied by dx, if you take the derivative of that with respect to y, and then the derivative of the expression being multiplied with dy, if you take the derivative of that with respect to x, and those two are equal, then you have an exact differential equation. Okay? All right, so that's just identifying whether an equation is exact. So let's do some examples where we're identifying that, and then hopefully we'll have time to solve for one of these problems. So, I didn't copy those, 1 through 26. I thought I had my book open already. All right, so I'm going to go to the book and look at problems 1 through 26 in this section, and we'll see if we can pick one. And that'll give us some practice also, kind of get used to doing some, what's that called? Partial differentiation. Let's start off with an easy example. And we don't want to do anything here other than to identify whether this is exact or not exact. So the first thing we want to do is identify the m and the n, if we want to do it that way. And the one being multiplied with a dx is going to be the m, and the one multiplied with a dy is going to be your n. And what you want to do is take the derivative of m, that's what the symbol means, take the derivative of m with respect to y. So if you take the derivative of m with respect to y, what you're doing is you're going to pretend that x is a constant, and then the variable is y. So if you pretend x is a constant, what's 5 times x? What's the derivative of 5 times x? 0, because x is a constant, so you're just pretending that x is a constant. So this is 0, and then the derivative of 4 times y with respect to y, 4. So that's equal to 4. And then on the other side we have n, and we want to take the derivative of n with respect to x. And I'm going to do it this way. The derivative of n with respect to x, what's the derivative of 4x with respect to x? That's 4. And what's the derivative of 8y cubed with respect to x? 0, because y is a constant with respect to x. So it turns out in this particular case that those two expressions are equal. And if they are equal, then we can conclude that this is exact. So ny equals to m, let's say nx is equal to my, and so that means that this is an exact differential equation, which means we would be able to solve for this using a technique that we're going to learn. Okay? Any questions so far? Let's do another example that might require a slightly more complicated partial derivative. Slightly, not a lot. Let's do number 5. So you can go ahead and identify the m and the n and call it m and n, or you can just say, oh, there's a dx over here, so I want to take the derivative of this thing with respect to y, right? Just the opposite. And there's a dy over here, so I want to take the derivative of this thing with respect to x. So any way you want to try to play it. Let's see. So my m is equal to 2x times y squared minus 3. I want to find the derivative of m with respect to y. This is the other type of the other notation. So I'm going to treat x as if it was constant. So what's the derivative of 2xy squared with respect to y? 4. The x is a constant, so you just leave it alone. And then y to the first power. So bring the power down. And then the derivative, the 3 is just a constant, so any way you look at it, that's going to be 0. Okay? Now let's take our n, our other expression. Now we need to take the derivative of that opposite of this differential y, so the derivative with respect to x. And with respect to x, 2x squared y What's the derivative of that with respect to x, treating y as a constant? For xy, and then we have another constant there. The derivative of constant is 0. So in this case, they do equal each other again. So this also is exact. Okay? So not everything will be exact. These two examples happen to be, which means we should be able to solve for this. Okay so far? All right. Now, these are differentials. These are derivatives, and there's derivatives of x's and y's. And so I just want to point back at this thing over here. We got this expression over here to be equal to f of xy, the derivative of f of xy. And so if we undo the derivative by taking the integral, then we should get it to come back to the original f of x. So that's the key idea. Oh, this transient term doesn't belong there. And so how are we going to solve for this type of differential equation? So no, doesn't say. I have to tell you, but I can just copy it. Okay, so we'll go back to this idea that f of xy is equal to a constant, and then if I take the differential, this would be the partial, what is it, m? It's the partial of f with respect to x times dx plus the partial of f with respect to y times dy is equal to 0, right? So that's we saw that a couple of slides ago. It's the same thing, right? I didn't change anything, did I? Is equal to 0. So if you translate this into the m dx plus n dy, right? Then you kind of have these things matched up. So it looks like m is equal to the partial of f with respect to x, and then n is equal to the partial of f with respect to y. So if I have this type of differential equation, this is your exact dE. What we want to do is we eventually want to solve for y. And so if we can come back to this, if we can find f, then there's going to be a y in there implicitly that can be the solution. So from here, what we want to do is we want to obtain f again. So in order to obtain f from here, I'm going to have my partial of f with respect to x. That means originally I took the derivative of f with respect to x. So if I want to obtain f again, what do I need to do? I need to integrate it with respect to what? X. So the check for exact was already done. So let's say we know now that this is an exact differential equation. And so now we want this thing, we want to obtain our original f. So since df dx is equal to m, and that's taking the derivative of f with respect to x, well, what if we take the derivative of this with respect to x? We're going to undo that derivative and go back to our original function f. So that means I have to do the same thing to this side. That looks really confusing from the previous slide, right? When we took derivatives with respect to the other variable. But now, taking the derivative with respect to the other variable is a check to make sure it's exact. Once you know it's exact, this is the process of solving for it. So likewise, our n is a derivative with respect to y. And so to obtain your original f function again, you would take the derivative, antiderivative, the integral of this with respect to y. And then we would need to match this up somehow. Okay? So that's, we're not finished with this, and we need to stop. So we're going to come back. I'm going to try to redraw this whole thing again so that we can start from scratch in terms of solving for this. Okay? There's supposed to be a quiz on Thursday, but I think the quiz is on integrating the first order linear differential equations, which is what we were doing today. So I don't know if it'd be good to give it on Thursday, so I think I'm going to give it on Tuesday. So the quiz is going to be on Tuesday instead of Thursday. Okay? Integrating factors.